Alright, this is the second lecture for Unit 4. Before moving on to the new topic, let's try a couple of practice problems. First practice problem, how much potassium carbonate, K2CO3, is needed to prepare 3 liters of 0.0155 molar potassium carbonate solution? Now generally in chemistry questions like this, when you're asked how much, mass in grams is wanted for the answer. Alright, attempt this problem on your own before moving on to the solution. If molarity is moles times liters, and that's the definition of molarity, then molarity times liters equals moles. And we could take the molarity, 0.0155 moles per liter, is how it is written here, and multiply by the volume, 3 liters. Notice units of liters cancel, and we're left with moles. This is moles of potassium carbonate. Moles is then multiplied by a conversion factor to convert from moles to grams. The molar mass of potassium carbonate appears in the numerator in grams. The denominator has moles of potassium carbonate. Moles cancel, and we're left with 6.43 grams of potassium carbonate. Note that as before, if you wanted, you could have done this calculation in one step. Molarity times liters times conversion factor from moles to grams. Now attempt this one. How much potassium sulfate, K2SO4, should one weigh out to make 500 milliliters of 0.1 molar K2SO4? So we're making a 0.1 mole per liter solution of K2SO4, and the volume is 500 milliliters. Attempt this before moving on. 500 milliliters has to be converted to liters. It's multiplied by a conversion factor of 10 to the negative third liters over milliliters to give us 0.5 liters. Volume, 0.5 liters, can be multiplied by 0.100 mole per liter, molarity, to give us moles of potassium sulfate. And 0.05 moles of potassium sulfate can be multiplied by a conversion factor from moles to grams, molar mass in the numerator over moles in the denominator, to give us 8.71 grams of potassium sulfate. This example is essentially the same as the last one, except it is necessary to convert volumes of milliliters to liters. Right, the new topic in this lecture is dilution of solutions. Now, dilutions are a type of calculation you will make many times in your career, whether you major in biochemistry, chemistry, or biology. Here is a typical dilution question. Suppose we take 0.0050 liters of 0.00642 KMnO4 solution. Okay, this is the molarity of the solution. Let me correct that and then we'll move on. 0.0050 liters of 0.00642 mole per liter solution is diluted with water to 500 milliliters to make solution number 2. Question is, what is the molarity of solution number 2? You can attempt this for yourself before moving on. Beg your pardon. Let's consider the dilution process. The number of moles does not change. Moles before equals moles after. Therefore, the molarity before times the volume before, which is equal to the number of moles before, molarity times volume, is equal to the molarity after times the volume after. This relation is often expressed MIVI equals MFVF. Initial molarity times initial volume equals final molarity times the final volume. Once again, MIVI equals MFVF. Let's consider this illustration of a dilution. We start out with a solution and dilute by addition of solvent, water. Clearly, I hope from the illustration, moles stay the same, moles of solute. Count the dots, that represents moles of solute. Final volume is greater than the initial volume, and initial molarity will be greater than the final molarity. Keep those tips in mind when considering employing this dilution equation. Right, once you have this, the relation MIVI equals MFVF, dilution problems become pretty straightforward. You may have already attempted the answer, but here's the answer using MIVI equals MFVF. I restate the problem here. 0.05 liters of 0.00642 molar KMnO4 is diluted to 500 milliliters to make solution 2. What is the molarity of solution 2? Right. Now we know MIVI equals MFVF. We identified 0.0050 liters as the initial volume and 500 milliliters as the final volume. 0.00642 molar is the initial molarity, and we're trying to find the final molarity after dilution. So I can represent that with a question mark. Rearrange the equation. The final molarity is MIVI over VF. Now, note what I have done here. MI is 0.00642 moles per liter. I put that here. The volume, V sub I, is 0.0050 liters. We were given the final volume in 500 milliliters. I have replaced that with 0.5 liters down here. We've already seen that 500 milliliters is 0.5 liters. I have changed the units. This assures that liters cancel, and we obtain units of molarity, big M. The solution is 6.42 times 10 to the negative 5. Once you algebraically rearrange the dilution equation to solve in a dilution problem, be sure that you have a consistent set of units. Liters for volume assures that volume cancels. Notice you didn't have to use liters. You could have expressed both volumes in milliliters and obtained the same result. Alright, this is an example of a dilution problem where you're asked the final molarity after a dilution. Let's look at some other types of examples. Here's another type of question. How would we make 25 milliliters of 1 molar HCl from a 3 molar HCl stock solution? Now, a common situation in laboratories is that a stock solution is what gets diluted to make a solution that you'll use in your actual lab. Its molarity is the initial molarity. The final volume of the prepared solution is 25 milliliters. Its molarity is the final molarity. So the final molarity in this problem is 1 molar HCl. So if we know the initial molarity, the final volume, and the final molarity, we must be solving for the initial volume. In other words, how many milliliters of stock solution are required? Right, now that we've identified all the variables, attempt the problem before moving on. Alright, solve for VI, volume of stock solution needed. VI is MFVF over MI, or 1 molar times 0.025 liter over 3 molar. Note units of molarity cancel here. And we have a volume of 0.083 liters, which can be converted if the problem asks for milliliter units of 8.3 milliliters. So take 8.3 milliliters of the stock solution and dilute with water to a volume of 25 milliliters. Note that I took the volume of 25 milliliters and converted it to 0.025 liters for this problem. Alright, here is yet another type of question. 50 milliliters of a sample of water is diluted to 1 liter. The concentration of PCB, polychlorbenzene, a pollutant, in the diluted solution is found to be 0.020 molar. What is the concentration of PCB in the original sample? All right. So a sample of water is diluted, and the concentration of diluted sample is 0.020 molar. Question asks for the concentration in the original sample. Right. 50 milliliters is V sub I. 1 liter is the final volume of the solution after we dilute the sample, V sub F. 0.020 molar. 0.020 molar is the final molarity. Just note I just corrected a typo there. 0.02 molar is M sub F. Question asks for M sub I. What's the concentration in the original sample? Note it's important to use consistent volume units. For this question, I'm going to use volume units of milliliters, so I note that 1 liter is 1,000 milliliters. Alright, at this point you could attempt the solution. Do that before moving on. Right, M sub I is M sub F times V sub F over M sub I, or 0.020 molar times 1,000 milliliters over 50 milliliters. The correct answer, is 0.40 molar. Notice that volumes of milliliters can be used if they are used consistently. In other words, for V sub F and for V sub I. And I'm afraid I had to pause to correct another typo there. The quantity in the denominator is V sub I. M sub I is M sub F times V sub F over V sub I. And we are expressing V sub F and V sub I in milliliters. Alright, here is one last example. 3 milliliters of 12 molar sodium nitrate solution is diluted to a molarity of 25.0 decimolar. What's the volume of the resulting solution? 3 milliliters is the initial volume. 12 molar is the initial molarity. The final molarity is 25.0 decimeters. I'm sorry, decimolar. Clearly the question is about what is the final volume? What's the volume of the resulting solution? Consistent units are also important for concentration. 12 molar is 120 decimolar, and I will use decimolar units to solve this problem. You should attempt the solution before moving on. Alright, here's the solution. V sub F, is M sub I times V sub I over M sub F, 120 decimolar times 3 milliliters is divided by 25 decimolar. Decimolar units cancel, and the correct answer for this dilution calculation is 14.4 milliliters. This concludes the second lecture for Unit 4.